which is fairly poor, and it's mostly due to some of the how these buffers are located in various structures in the kernel as compared to user space, where things are mostly just on a stack and not within a struct itself. And actually, Spender has helped out with fixing this and submitting some patches, or at least some knowledge upstream to the GCC developers, so that the built-in object size will be more effective in the future, not only for kernel but also for user space too. So we should hopefully see this, increasing as time goes on. Also, you have kernel heap overflows. In the Linux kernel, you have 3 types of allocators, which are all very similar. Some are just targeted at slightly different allocation models. You have the SLAB, SLUB, and SLOB allocators, and I think there's one more too that was recently developed. SLUB is the one that's used by default on these kernels. It used to be SLAB, but they transitioned over to SLUB, and it provides, the kmalloc, k-free family of functions. And we could spend an entire talk talking about the intricate details of these allocators. Larry H. in Frac66 wrote an awesome article essentially summarizing, 66 was pretty recent too, so it was essentially summarizing the history of all the allocators and going through the various exploitation conditions, which are pretty standard if you are used to exploiting a heap, unsafe unlinking vulnerabilities. Now there is Kern Heap, which was just released a few months ago, which is a heap production from the guys at Subreption, also Larry, which provides this metadata protection, safe unlinking, protection against double freeze, checking of uninitialized memory usage, a lot of different functionality that can harden your kernel against these heap-based overflows. The one that people have gotten way overly excited about in the past maybe year or so is these null pointer dereferences. And calling it null pointer dereferences is actually wrong. Well, it's not wrong, it's just not completely accurate. These are userland pointer dereferences, of which null is just a very specific case. Just happens to be the address 0 as opposed to the address 20 or the address 25. And it just happens to be that these null pointer dereferences happen due to the common programming mistakes you make in a C or C++ based language, and the ones where you might be dereferencing a pointer somewhere else in the userland address space, is not as common as a programming mistake. But in these shared VM architectures, you can see that in your virtual memory space, your user address space is shared with the kernel space. So the kernel sits at the top or the bottom, however you rotate it, of the address space, and is protected from being accessed or modified by the user address space with its page permissions. But what can happen is when you call into the user space code, if you can trick user space functions into dereferencing a pointer into your user address space and you control the data at that pointer, you can do some interesting things. So traditionally, this is done with a function pointer dereference, where the kernel will attempt to call a function located at a address that's controlled by user space, which essentially you put your shellcode there, and it will jump to there and execute your code with the permissions of the kernel. Or in less common cases, you'll have data control where the kernel will dereference maybe during an assignment to a pointer in user space, and you'll later be able to control maybe an arbitrary write or some other method of elevating your privilege from that initial data control. So the traditional pattern goes like this. If you have a null pointer dereference of a file pointer, you would set up your payload, you mmap the null page into your address space. Normally, if there was a dereference of a null pointer, it would be an illegal operation, of course, a segmentation fault. But in this case, we're making the 0 address valid. So any memory that's dereferenced there is just like a normal memory access. And we can copy our payload to that 0 address. We do whatever we need to trigger the null dereference. In this case, this is the famous sock send page example, which is triggered with the a send file. And then when the null dereference function pointer is actually dereferenced, it will call into your shellcode at address 0. Your shellcode would then walk the credential structures of the kernel memory and maybe change your UID to 0 or whatever other payload you want to execute. And if you want to look at exactly how easy it is to write one of these vulnerabilities, you should look at Spender's Enlightenment framework, which really you just fill in two functions sort of a prepare function for before the exploit, and then a trigger exploit, or trigger function to actually cause the null dereference, and then it will execute its own built-in payloads, which are all cross-platform and disable every single security mechanism in the kernel as possible. So what I'm going to talk about right now is actually an example from OpenBSD, which I realize is completely cheating and betraying my talk title. But I like this one because it was multi-stage and it had some cute tweaks about it. The git sock op call for OpenBSD's standard IP sockets had an issue where we could eventually get a controlled write of just the value 1 at an arbitrary address. So you might not be clear from this code output here, but this macro actually was expanding to a null dereference and then writing a 1 to a particular address under our control. So breaking down the exploit, how we would actually leverage this into a privilege escalation, we would call a map to map our 0 page. The kernel would go ahead and map that. We would set up a fake mbuff, which was the structure here that's being operated on in this git sock opt code. We would set this up with a fake mbuff at the null pointer, such that one of the offsets, which is the data member of this mbuff structure, would contain the address of a memory address that we want to write to. So in this case, we can pick a system call table entry, which are predictable and static on OpenBSD. Next, we actually want to trigger this vulnerability with the git sock opt, which causes the kernel to access this fake mbuff located at 0. It has no idea that this is actually an mbuff that was created by a user. It thinks that it's just a normal part of its kernel memory. And it looks at the address stored in our data field and writes a value of 1 to a syscall entry in the syscall table. Now, what's special about 1? You know, how can we leverage that into actual privilege escalation? Of course, 1 is no different than any other address. We already have the 1 address mmapped from our original mmapping of the 0 page. So all we need to do now is just copy our shellcode to the address 1, and then call the system call that we overwrote in the system call table here, which is now pointing at the address 1. And the kernel will dereference the system call, pop over to 1, and execute our shellcode, which is located there, which will then traverse the credential structure and set our process to UID 0. So it's a little extra couple hops than a traditional null pointer dereference, but I thought it was interesting and worth sharing, even though it was OpenBSD. So there's a couple different protection mechanisms to stop these type of userland dereferences. The one that is targeted at this rash of null pointer dereference vulnerabilities is the mmap minadder support, which just basically disallows you from mmapping any to any addresses that is lower than this value. So essentially, if it's set to say 4096, we can't actually map anything below that. We can't map the null page, therefore preventing a lot of these attacks from being exploitable. They still are denial of service conditions, but we can't actually hijack the control flow of the kernel. Now this blocks, of course, all the null pointer dereferences, but not all user dereferences, and in fact has been defeated multiple times by Tavis and Julian via a couple different mechanisms here, which were able to bypass this protection, since there are several code paths which allow you to map pages from user space that don't necessarily go through the same code paths that are protected by this mmap minadder. The more comprehensive solution for these user space dereferences is called uderef, appropriately, which is part of Spender's GR security patch set. And on i36, it uses segmentation to enforce these boundaries between kernel space and user space and catch these null pointer dereferences. And actually, just a week or two ago, him and Pipax released support for 64-bit, which is a little more difficult due to the lack of some of these segmentation features that were discarded on the AMD 64 architecture. But it does protect against some of the most common scenarios of these user space dereferences. Of course, there's also things that don't necessarily result in actual privilege escalation immediately. Memory disclosure is one of the, I'd say, underrated bug classes in the Linux kernel. What we can do is actually leak sensitive kernel memory back to user space, and this is most commonly done with a unbounded copy to user operation, which is in charge of taking memory from kernel space and copying it hopefully safely, to user space. And of course, you can pair this up